We're to talk a little more about growth and compounding, but now we're going to try it in reverse just to shake things up a little bit. Last time we calculated that 500 growing at 5% per year for 15 years is going to be worth 1039.46 at the end of the period. Now, so if somebody asked you, okay, 500 were invested at an interest rate of R for 15 years and it's worth 1039.46 at the end, what was the interest rate? Solve for R. You can figure that out. I mean, we just did it. The answer is obviously 5%. But if we hadn't just done the calculation, if we faced some general problem, how would I find the answer? I got to do a little math. Set an equation, 500 times 1 plus r to the 15th power equals 1039.46, and solve for r. How to do that? Well, remember algebra. If I have some number x to the 15th power, how do I solve for x? I got to take that whole thing to the 1/15th power. That's 1 over 15 power. I mean, you remember doing that for lower powers. If you had x squared equals something, you solve by take the square root. And remember, the square root is the 1/2 power. So you just remember your algebra. Now we can ask the question how to find z given that some amount z is invested at 5% for 15 years and worth 1039.46. That's a little bit easier with the algebra. You know, z equals 1039.46 divided by parentheses 1 plus 0.05 all to the 15th power. Now, the reason we're doing all this in reverse is because we often want to do discounting, which is discovering what is the value right now of some amount of money in the future. For now, we're going to ignore things like risk or inflation, can add those complications later. Start with a really simple case. How much money do I need today to invest at some interest rate to get some W dollars at some date in the future? Basic microeconomic theory, the value of something is the opportunity cost. What do I have to give up in order to get something? In a simple case, if I can put $100 in the bank today at a 3% interest rate and get $103 in 1 year, then the value of $103 in a year is $100 now. That's how much money you have to give up right now to get $103 in the future. That's called discounting because the value goes down. $1 in the future is not worth $1 today. $1 in the future is worth less than $1 today because of opportunity cost, because interest rates. Put this problem into some more mathy terms. After t years, z dollars initially becomes z times 1 plus r to the t power. How do we find the present value? Well, w equals z times 1 plus r to the t power and solve for z. Z is w divided by 1 plus r to the t. Rewrite as w times 1 plus r to the minus t. Review a little bit about how exponents work, but it's called the present value, and it comes up again and again and again in finance applications. Because a lot of what Wall Street is doing is just saying, okay, somebody get money in the future, how much is that worth right now? At the start, I noted a lot of finance is translating the value of money now versus the flow of money in the future. The flow of money is just worth the sum of a bunch of present values. That's what discounting is. It's all it is. Now, since the value is going down and down as the time to compound goes up and up, we might suspect it could converge to some value as time goes to infinity. Yeah, like last time, we're going to do an infinite number of times. What is the value of W dollars paid next year and the year after and the year after that and the year after that, on and on and on forever? We use our little math brain, algebra brain, to know the way exponents work. If I take some number bigger than 1 and square it, then it gets bigger. If I take it at the 10th power, it gets a lot bigger. Take it at the 100th power, it gets a lot bigger. So forth. But that's in the denominator, however. 1 divided by some giant number, which gets closer and closer to 0. The sequence of terms here, w over 1 plus r to the first, plus w over 1 plus r squared, w over 1 plus r cubed, on and on and on to the t power. As t gets bigger and bigger, that term is going to get smaller and smaller. It's reasonable to think it might converge to something. So we'll just suppose it does converge to something, call it x, and then do a little bit of algebra to solve for x. Find x equals 1 over r. So if r is 5%, then x is 1 divided by 0.05. So that's 20. That easy. Now, if R is 4%, 1 divided by 0.04, that's 25. As R gets bigger, X is smaller. Again, that's a common feature of discounting. Now, there's another way of thinking about it, perhaps a little more fun. Suppose I win the lottery. And we'll say it's a $10 million, so not Powerball win, but still, if I didn't win, how much can I take out every year forever if I never touch the principal? Obviously, that depends on the interest rate. If the interest rate is 10%, then if I got 10 million in the bank, I can take out $1 million a year and never touch the principal. If the interest rate is 5%, then I can only take out $500,000 a year. If the interest rate is 3%, then I can take out $300,000 a year. So going back to the opportunity cost argument, what's the present value of $300,000 paid each and every year forever if the interest rate is 3%? That's 10 million. So these different viewpoints provide the same answer. So interest rates are the price of the future. When making rational choices about the future relative to present, we'd use an interest rate to discount the future values, whether costs or benefits. Benefits in the future are worth a bit less because they're not benefits now. But same for costs. The ones in the future are worth less than right now. And that's important in sustainability calculations. Absolutely. A corporation might have an opportunity for a big payout in the future, and they want to figure out how much is that worth today. Maybe it's a biotech company that plans that in 15 years they'll launch some product that'll make a lot of money. How much is it worth to spend right now to develop that? When they pitch to investors, that's one of the key questions that investors have to figure out. The whole financial system is figuring out how to transform a flow of payments into a single value. Depends on interest rates. The value of an amount of money in the future, that depends on the interest rate. A high interest rate means a higher discount rate, so future money has a higher discount and is going to be worth less if interest rates are higher. So the present is going to be more valuable relative to the future if interest rates are higher. The whole society, trying to make rational choices, has to figure out the trade-off between costs and benefits at different times. What interest rates should be used? That's a thorny ethical question. But high interest rates mean the future gets a lower value. That seems like age discrimination. People who were or even have yet to be born later in time get a higher discount than the people currently living. It's a complicated issue. Now, we've been using percentages. Let's do a quick review. Hopefully this is a review. A percent is a convenient way of writing a decimal. You just move the decimal point. 15% is 0.15, 99% is 0.99, 150% is 1.50. Just move that decimal point over. 1% is 0.01, 0.3% is 0.003. It's very mechanical, just moving the decimal point. But you read about things like US inflation data is commonly reported as, for example, 0.2%, which means 0.002. That's the change over 1 month in the price level. So, that's kind of tough to figure out. And we also use percentages to compare two numbers. If A is half the size of B, then A is 50% of B. If A is quarter the size of B, then that's 25% of B. If variable is increasing, there are a number of ways of expressing that. If Z is 125% of the size of Y, then that means Z is Y plus 25% increase, or Z equals 1.25 multiplied times Y. And, sometimes you got to look a little bit extra carefully just to make sure you're not going fast and getting sloppy. A lot of stores, they're putting stuff on sale. They count on the fact that people are fast and sloppy and thinking. A store might advertise sale, 50% off, and then take an additional 25% off. Sounds good, right? But does that mean you get 75% off? No. There's a trick. It's right there in the words, but you got to read the words carefully to see the trick. Think about the extreme version. If they've offered 50% off and then take another 50% off, would that mean they're giving away for free? No, that means you're getting it for a quarter of the price. They're taking half off and then another half of the remaining half. Half the half is a quarter. So they're offering a total of 75% off if they say take 50% off and then another 50% off. Going back, then an offer to take 50% off and then another 25% off means you take half off at the beginning and then a quarter of the remaining half, which is 1/8. So in decimals, you'd get it at 37.5% of the original price. I mean, similar question, what is 10% of 10%? You don't multiply 10 times 10, and if I get 100, that's not 100%. No. You got to convert to decimals. So 0.1 times 0.1 equals 0.01. That's 1%. So 10% of 10% is a tenth of a tenth. That's 1/100th. That's 1%. You just got to be careful. Another thing to remember is exponents and logs. You've probably heard news items about some movie star or sports star getting paid, and you hear phrases like they signed a 7-figure deal, which means that person got paid 7 digits worth of money, some amount between $1 million and $9,999,999. So they're implicitly using a log scale. And we can measure our own salary in the same way. But you and me and most people we know are getting 2 digits per hour. That's not as exciting. But, somebody graduating might get paid an annual salary in the high 5 digits, and after a few years of work, get to 6 digits. That's using a log scale implicitly, log base 10. Now, of course, from math, we often use log base E because, well, lots of reasons, the math works better, blah, 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 details. It's related to the fact that E to the R would have a constant percentage growth rate. So on a log scale, we just give a line. So that's one of the reasons in graphs, we often show things on a log scale. So the constant growth rates are just a straight line.